When we talk of the graphic system, there are two main types that are available. So we have the non-interactive graphics, computer graphics, and also we have the interactive computer graphics. So anytime we talk about the non-interactive computer graphics, we term this type of computer graphics as passive, and for the interactive computer graphics, we term it as active. Now, we say a non-interactive computer graphics is passive mainly because in this type of computer graphics, the picture which is displayed or produced on the monitor does not really interact with the user. So in other words, the picture is produced on the monitor, and also the user does not have any control over the images that is displayed on that monitor. So that is the user cannot make any kind of change in the rendered images displayed on the monitor. A typical example of a non-interactive computer graphics which is passive is the titles that are shown on our TV. So for example, on our TV, we probably will be watching a program on TV3 where the titles or the information or the screen displays everything that is happening per the program. If it is a movie that is we're watching, the movie is displayed to the user, and in this case, the user who is sitting behind the computer or the TV does not interact with what is displayed on the screen. So TV3 will give out an example, maybe a date rush. TV3 will come out with date rush, and at the end of the day, the information that is displayed on the screen, the user seated does not control anything that happens with the program that is being shown by TV3. And again, non-interactive computer graphics involve only one-way communication between the computer and the user. So the user can see the produced image and cannot make any change in the image that is displayed. So anytime you think about a non-interactive computer graphics, you should think of it being as passive. And if it is passive, then it means the user does not have any kind of control over the image that is displayed on the screen. Another example is the screensaver that is also displayed on our computer monitor. So for example, we can have a screensaver that is displaying flashes of pictures on the screen. So in that case, the user just sits behind the computer and does not have any interaction with the screensaver or the images that are displayed within the screensaver. Now, when we talk about interactive computer graphics, this time round it is active, so it means it involves a two-way communication between the computer and the user. So here we can have the observer that gives some sort of control over the image by providing him with an input device. For example, those that play video games, you have a controller in your hands that you use to interact with the characters or the characters that are within the scene in the computer game. Just like in FIFA 2020, those that play game, or even Mario, you have a joystick in your hand which you use to interact with the character to move it to the left, right, and the rest. So this actually helps the observer to signal his request to the computer. Now, the computer, on receiving the signal from the input device, which probably is the joystick, can modify the display picture appropriately. So for instance, if it's supposed to kick a ball, you can use the joystick. You press a key on the joystick on the controller to change the current leg position of the individual. So to the user, it appears that the picture is changing instantaneously in response to the command that he gives. So he can also give a series of commands where each one generating a graphic response from the computer. So in this way, he maintains some sort of conversation or dialogue with the computer. So interactive graphics generally affects our lives in a number of indirect ways. So an example would be it helps us to train the pilots of maybe an airplane which I explained some time back in terms of simulation. So we can create a flight simulation which may help the pilot to get trained not in the real aircraft, but the real aircraft, but on grounds at a control of a flight simulator. So in this case, the flight simulator serves as the mock-up of an actual aircraft flight deck, which contains virtually all the usual controls that will surround an individual who sits behind the actual aircraft to control or take or fly the plane. So most of the time we have the flight simulators having many advantages over the real aircraft for training purposes. An example would be the burning of fuel. So for instance, we will save fuel if we were to simulate, if we were to find a way to simulate the aircraft, how to fly an aircraft. And again, in terms of safety, we don't give chance to having to we don't give chance to getting accidents if we should use the simulator to learn how to fly a plane. And usually the ability to familiarize the trainee with also a large number of airports. So you can have so many airports that are simulated, maybe an airport, maybe Kotoka International or Murtala International Airport. You can have a simulated version for the aircraft for the pilots to learn how to fly and land on such airports to make things easier for the training pilots. So anytime you think about interactive computer graphics, you should always have it in mind that this type of computer graphics is active, and it is active in the sense that it involves a two-way communication between the computer and also the user. Now, there are three main basic components that you should always have in mind when we talk about interactive computer graphics system. Now, these are the input, the processing, and the display as listed over here. So you can see an example of some examples of the input devices that are used as the basic components of an interactive computer graphic. And over here we have the processor, where of course, if the processor being the brain of the computer, we also have a memory to help save some of the things that we will do to aid the inputs that we put in the processor to process. And of course, we also have the buffer frame in terms of an image formed in the buffer frame. So if we should have we're working with the computer graphics, the images that is formed and displayed on the screen is saved in the buffer and the frame buffer. Now conceptually, this is how the conceptual framework for an interactive graphics looks like. So in this case, we have the application model, which sometimes is termed as a database. We have the program that is going to help run on the computer graphics library. We also have the graphics system, where we have the GPU located. Then finally, we have the monitor that displays the information that we want. Now, the conceptual framework that you see here is segmented into two main parts, and it's being divided, as you can see, with the dotted line over here. So we have the software part, which involves the application model and the application program together with the graphics library, and the hardware parts, where we have the GPU to help process the rendering of images on the scene which we see on our monitor or screens. Now, the graphics library or the package serves as the intermediary, as you can see here. It serves as the intermediary between the application and also the applications that we have here, and also the display hardware, which is the graphics system. And of course, the application program that you see here maps all the application of objects to images or views. So the application program that you see here is responsible for mapping all the application objects to view or images of those objects by calling or sometimes invoking on the graphics library. So the application model may contain lots of non-graphic data. An example of non-graphic objects properties also will reside in the application model. So still in the same way, now we have the graphics library serves as the intermediary between the application program and also the display hardware. So in the same vein, we also have the user interaction results, which is more into the modification of the model or the images that will be displayed on the screen, which would eventually be a 2D object that will be displayed on the scene on the screen. Now, this hardware and software framework is more than about 4 decades old, but it's still useful whenever we talk about computer graphics. So for the conceptual framework, this is how the interactive graphics looks like. Of course, it is an old architecture or framework, but it still works in our current state. Now, still moving on, we have display devices. There are lots of display devices that are available. So anytime we think about display devices, what comes in mind is the output devices. And of course, the output devices are the ones that are going to display the information to us. From the conceptual framework, the display of using the graphics library, we eventually would have to find a way to display the images that we create in a 3D world on the monitor or the screen. So the most popular or commonly used output device in the graphic system is the video monitor, which we term as the normal computer monitor or display monitor. Now there are some types of display devices that are available. You have the cathode ray tube, which you have learned in your physics class. You have the random scan. You have the raster scan. You have the colored CRT, sorry, that is the cathode ray tube. Of course, when we talk about the cathode ray tube, this is the old one, which is the black and white TV that we already know. So in this place, we're going to combine the two. Now, apart from that, we also have the direct view storage tube. That is the DVST. Then along the line, we moved on to the flat panel displays that some of us have in our homes. We also have the plasma panel display and the LCD, which is the liquid crystal display. Now we're going to talk about each one of them so you get to know of its properties and some of the advantages and disadvantages in the display devices that you see in here. Now let's take the first one, which is the cathode ray tube. So the cathode ray tube, which is normally termed as CRT, is some sort of technology which is used in traditional computer monitors and television. I'm sure most of you probably are were born somewhere in the 2000s, so you might have seen the cathode ray tube TV. That is sometimes the black and white. We also have some cathode ray tube TV that are also colored. Now the image on the cathode ray tube display is created by firing electron guns from the back of the tubes to some sort of phosphorus coated lining towards the front of the display. I will show a graphical representation of that. So once we have the electrons which have been fired from the back of the tube, the electrons are deflected or moved in such a way that they hit the phosphorus the phosphorus that is on the screen of the cathode ray tube. So upon hitting it, they light up and are projected on the screen. So the color you see on the screen is produced by a blend of these three colors. That is the RGB, red, blue, red, green, and blue. These three colors are combined to give us the color that we see on the screen of the cathode ray tube. Now, the stream of electrons is guided by magnetic charges. Of course, when a gun fires, it needs to be guided to hit the exact point on the screen to display the exact character, the exact picture or pixel that we need to view on the scene. So the stream of electrons is guided by a magnetic charges, which is why you get some sort of interference when you have a shielded speaker or magnetic devices that are placed close to the CRT TV. Those that have had the chance to experiment with this, those in the olden days, the black and white TV and even the colored cathode ray tube TV, when you have a magnet and you take it, you move the magnet close to the screen of the TV set, you see that there is some sort of deflection or distortion that occur in the pixels that is displayed on the monitor, and the reason is we have magnetic charges within the cathode ray tube that help guide the rays to hit the exact places on the screen. Now, this is how the cathode ray tube looks like. I intentionally brought different variants of the tube that came out from online. So we have the connection pins, we have the electron gun being fired from this point and passing through the focusing system. Then we have the horizontal deflection plate to help guide it horizontally, and eventually we also have the vertical deflection plate to help guide the ray vertically to enable it to hit the exact place on the screen, which is coated by the phosphor coated screen. So this is the electron beam that is emanated from the back of the tube. So in the same vein, we can also see the same drawing also. Located somewhere here. This is the TV, and we have the tube having some sort of magnetic system to help deflect the rays or the beam that come from the back of the tube. Now, the lights emitted by the phosphor fades rapidly, and because of that, we have something we call the refresh CRT. So one way to keep the phosphor glowing is to redraw the picture repeatedly by quickly directing the electron beam back over the same point. So because it fades when the beam hits on the phosphor, it fades quickly. There is a way to refresh the phosphorus to glow again in order to draw the picture that is supposed to display on the screen. Now, this is also another picture of the cathode ray tube. So this is the TV, and these so from the TV we have a section of it has been displayed over here. So these are the beams in the form of RGB, so red, green, and blue, that hits on the phosphorus that is coating the screen to display the pixel that we need to see. And in the same way too, we also see from the tube, the back of the tube, this is how we have the electron gun also firing up the beam from this side And these are the things that are involved in it. Now, in an exam, I'll expect you to at least draw this and explain how the cathode ray tube works. So, just as I've said, we have the electron gun consisting of a series of elements, primarily heating up the filament at the back and the cathode. So now the electron gun creates some sort of a source of electrons which are focused into a narrow beam directed at the face of the cathode ray tube. We also have a controlled electrode which is used to turn the electron beam on and off. Now within that same, we also have the focusing system, which is responsible to create a clear picture by focusing the electron that is produced into a narrow beam. Then within that, we also have the deflection yoke, which is used to control the direction of the beam that is produced, the electron beam that is produced. So it creates some sort of electric or magnetic field, which blends with the electron beam as it passes through the area. So in most of the conventional cathode ray tube, the yoke, which is the deflection yoke, the yoke itself is linked to a sweep or a scan generator. And this deflection yoke, which is connected to the sweep or the scan generator, creates some sort of fluctuating electric or maybe magnetic potential. And finally, at the phosphorus coated screen, where we have what we have over here, the inside front surface of the CRT is coated with phosphorus. So the phosphorus glows when a high energy electron beam hits them. As I told you, the beam comes in these three colors, RGB. So the phosphorescence is the term which is used to characterize the light given off by the phosphorus after it has been exposed to the electron beam. So these are the general explanation of how the cathode ray tube works, which I have explained over here. So this is also the same way. This is how the cathode ray tube works, and this is a diagram of how it works. So I advise you go through it and know how the cathode ray tube works. In case you are asked in exam, you should be able to explain how it works. Now we've talked about the cathode ray tube as the first type of display available when you talk about the computer, the graphic system, in terms of the output. Now let's talk about the second one, which is the random scan display. So the random scan display uses an electron beam which operates like a pencil to create a line image on the CRT. So the picture is constructed out of a sequence of straight line segments. So assuming this is our screen, the picture which we create are constructed out of some sort of sequence of line segments. So usually it is used mainly for straight line images. So for instance, if you want to draw a triangle, for instance, we have an electron beam which operates just like a pencil that hits the starting point of the creation of the rectangle. Then once we are there, we move on to the other one, each part of the rectangle to create the rectangle. Now, as I said, it is used as an electron beam which operates like a pencil to create a line image on the CRT screen. So the picture is constructed out of the sequence of straight line segments. So we have straight line segments helping us to create this picture. I told you every computer graphics library or application have its own primitive in the creation. Some are in the form of lines, others in the form of triangles and the rest. So the random scan used mainly for straight line images. So when we want to construct straight line images, we can use the random scan. So at this point, each line segment is drawn on the screen by directing the beam to move from one point on the screen to the next, where it is in the x and y coordinates that defines each of the points. Of course, still drawing the triangle, we can have it here. So it moves onto the points like beam moves onto the screen to draw each part of the shape, which is a line segment on the screen. So after the drawing of the picture, the system recycles back to the first line and design all the lines of the image. So let's take a typical example of how it works. You should also, you should also be mindful that this usually happens between 30 to 60 times within. This usually happens about between 30 and 60 times within a second. Now this is how the random scan display works. So from here, as I told you, it works just like the CRT. So in this case, we have the electron beam being fired from the tube to the screen. So this is the screen, as you can see, this is the screen. So we have the electron beam being fired from the tube to the screen. Now this time we want to construct a triangle. So it hits the first point of the triangle, the first point where the triangle will begin to construct. And I told you the random scan is used to draw line segments. So once it gets to this point, the next is to draw this line, the line, which probably will be this. So in this case, that is how it's being displayed over here. So the beam keeps drawing on the screen until it gets. So this is the test side. It keeps drawing on the scene until the line the beam or the pencil-like beam gets to the starting point, the initial points where the display started. So at the end of the day, the electron beam which is being fired from the tube starts here and draws the triangle which we want to construct on the scene. And the final destination will be to bring the beam to the starting point of the creation of the triangle. So the random scan monitor are also sometimes termed as the calligraphic display or vector display or stroke writing display. So in an exam, if I ask you briefly explain the stroke writing display, you should know that I'm talking about the random scan. Alright, as I told you, it is a line segment which is used to draw line segments. So the random scan display are designed to draw all the components of the line of a picture 30 to 60 times each second. So assuming we have the teacup over here or a kettle that you see over here, you can see this is the cathode ray tube. So electron beam is fired onto the scene, onto the screen, and because it's a line segment drawing, it draws the kettle in the form of light. So ideally, let me use this as an example. Ideally, this is supposed to be the ideal drawing. Now in using the random scan, in producing it as a random scan display, these are the steps that it will go through. It's a line segment, so it starts from here. It draws each part of the ideal drawing that is supposed to come on. all the ways. So it draws all of that, as you can see here. So in actual fact, we use it. The vector drawing is done. We eventually end up with a vector drawing because we are using the computer. We are the beam, the line, the beam is being shot onto the screen to draw each of the line segments, which this is what we wanted to draw. And at the end of the day, these are the steps that we go through to draw the objects that we see, the ideal objects over here. So it's a vector drawing. So each of the line segment that we see is more or less also found on the XY plane, and each of them have their individual coordinates in the drawing of these lines to eventually come out with the ideal drawing that we want over here. So that is about the random scan. Of course, the random scan also has some sort of advantages and also disadvantages. For an advantage of the random scan, we have the CRT. We have a CRT that has an electron beam directed only to the part of the screen where the image is to be constructed. You will realize that when we want to draw an image, we want maybe the triangle, as I use an example. The beam does not hit on each part of the scene of the screen to help construct the object that you are looking for, but rather it moves to the starting point and draws the object as we see, as we have seen, or as it had been depicted in the previous slide. Now again, as an advantage for the random scan tool, it also produced smooth line drawings. So that was obvious, and was able to produce smooth line drawing because it's a line drawing, because it deals with line drawings. And finally, the image that is constructed on the screen by for a random scan display has some sort of high resolution. So for instance, those that have used this Illustrator before, you realize that when you construct, when you draw maybe a logo or you draw a rectangle using Illustrator, you are able to stretch the rectangle to a very high. You are able to stretch it or zoom into the rectangle, and you still would see a very high quality rectangle being drawn. But other scan displays or other displays would not really, would actually pixelate along the line. So when we use a random scan, for a random scan display, the images that we produce are always of very high resolution and of high quality. It has its disadvantage, and the disadvantage is a random scan monitor cannot display realistic shaded scenes. So for instance, this is an object that we want to draw. This object is quite realistic, but if you use a random scan display, we're unable to come out with some sort of realistic shaded scene because it's a line segment drawing. We would have our objects in this form. Of course, we will not be able to have some sort of realistic objects that are created in the scene for us to see on the screen. Alright, so that is about the random scan. Now let's move on to the next one, which is the raster scan display. For the raster scan display, it's a little different from the random scan. So in the raster scan display, we have the electron beam sweeping off across the scene, one row at a time, from the top to the bottom. So for instance, if this is our scene, for the raster scan, the beam would have to sweep off each row on the screen. So all the rows on the scene, on the screen, would have to be swept up by the beam, one row at a time, from the top to the bottom. In fact, this happens very fast. So as the electron beam moves across each of the rows, the beam intensity is turned on and off to create a pattern of illuminated spots. So for instance, if we want to draw a character like, let's say we want to draw A or maybe B, the character B on the screen. We want to draw the character B on the screen. Because the electron beam sweeps off in from one row to the other, to start at this point, move to the other end, and keeps moving from the top to the bottom. Now, as the beam moves across each row, the beam intensity is turned on. So at this point, when it gets to this row, the intensity in drawing the B, let me deepen it a little. In drawing the B character, forgive my drawing, the intensity whilst the beam flows, so is swept off on the row, the intensity over here all would be turned off. But when it gets to the point like this one, which is supposed to draw the character B, the intensity increases. So at this point, the intensity increases on the screen, and of course it will increase on the screen again. So at this point, the intensity is turned off. At this point, the intensity over here are all turned off. So coming back again, when it's going to draw this next row, the moment it gets to this particular point, the intensity is on, on, just like that. So all these intensities will be off, and all these intensities will be on to help display the character that you want to draw. So the picture definition is stored in a memory area, which we term as the refresh buffer or the frame buffer. So the memory area holds the set of intensity value for all the screen points. So the memory area, which we term as the refresh buffer or the frame buffer, will hold the set of intensity, which whether on and off, for all the screen points. So the intensity that is electronic beam displaying will be saved in the frame buffer or the refresh buffer. All right, so this is how the raster scan looks like. So the stored intensity values are then retrieved from the refresh buffer and painted on the screen, one row, which is termed as the scan line at a time. So that is how this is, assuming this is the monitor. So all the rows that we see, that's like all the horizontal rows, all the rows that we see are termed as the scan lines. Now, the horizontal retrace are the diagonals that you see between each of the scan lines. So the dotted ones that you see are what is termed as the horizontal retrace. Once, as I said, once the rows are drawn from the top to the bottom, the moment it gets to the bottom, the beam is sent back again to the starting point of the row to keep to maintain the picture from vanishing from the screen. So this is the vertical retrace, as you can see here. So that is the line going back again to the starting points of the beam. So each screen point is referred to as a pixel. So in drawing the B, as you saw here, each screen point that is turned on is termed as a pixel. And of course, the screen has so many pixels, but we don't know whether the intensity will be on and off. So depending on the character that is displayed, we will know if the intensity is on or off. So each screen point is referred to as a pixel. So a pixel is more or less the picture element, the basic picture element that displays on the screen. So at the end of each of the line, the electron beam returns to the left side of the screen to begin displaying the next scan line. So that is by using the vertical retrace. At the end of this, it goes back again to the left side of the screen, which is this side, to begin the display of the next scan line. Now there are two main types of raster scan display. We have the interlacing scanning and the non-interlacing scanning. Well, the types of scanning or traveling of the beam, these are the types of scanning or traveling of beam in the raster scan. So there are two main types: the interlace scanning and the non-interlace scanning. Now, when you talk about the interlace scanning, the interlace monitor most of the time are relic from early televisions where we have the electron beam technology, GAN technology, being sufficiently primitive to allow, to not really allow quick drawing of entire screen. Now, here under the interlace scanning, each horizontal line of the screen is traced from the top to the bottom. Due to this, the fading of the display of the objects may occur because we have to draw each horizontal line of the screen. Because it is traced from the top to the bottom, it gets to a point where there is a fading of the display of the object occurring. So, for instance, it draws that line. It keeps drawing. Of course, it's a beam. It keeps going and coming and going and coming to draw all of this. So it gets to the point the intensity of the beam goes down. It fades along the line if you're supposed to do it. Once the intensity hits on the phosphorus, it keeps going. It gets to a point the intensity that is displayed whilst it's running will be faded from where it's actually started. So this is a problem, and it can be solved by what you term as the non-interlace scanning. We'll talk about that. So in this first, to solve this, all the odd lines are traced or visited by an electron beam. So this is 1, 2, 3. So all the odd lines are traced or visited by an electron beam. Then in the next cycle, it tries to trace all the even lines that are located directly under the odd lines. You should also be mindful that if the refresh rate was somewhere 30 Hz or cycle per second, then each pixel can be visited at most once every 1/60th of a second. So let's look at this. Of course, to remedy the fading, we talked about having using the non-interlace scanning. So the non-interlace monitors are now fairly standard, and every scan line from the top to the bottom is drawn in each pass. So the refresh rate usually is between 75 Hz and higher they are higher in these days, and the reason is to help assist the graphic accelerator card to render any crisp image that is or animation that is formed on the screen. So this is how to prevent the fading of objects occurring, we solve this by using the non-interlace scanning. So this is how the non-interlace scanning also looks like. So at this side we have the interlace display refresh rate of 30 frames per second is normally used, but it gives some sort of flicker. So for interlace display refresh rate usually is around 60 frames per second is normally used. So as I said, in the drawing of the electron beam, to avoid the fading of display of objects occurring, we solve this by using the non-interlace scanning. And by doing that, the odd rows, so you can see the odd rows are now drawn first. So the beam draws the odd rows first, and once it's done, then it comes back to draw the even rows. So for interlace, you can see over here we have this drawing the odd, then coming back again to the third. So this is the first row, this is the third row, going back again to the fourth row. So once it gets to the bottom, then it comes to the second row, goes to the fourth row to draw all of this. That is for the interlace. So for the non-interlace, of course, the drawing is done directly to avoid the flickering on the scene, the flickering of the object on the scene or the screen, sorry. Of course, the raster scan also has advantages and disadvantages compared to the random scan. The first advantage is it's able to draw realistic images. We should be mindful that we said that the random scan as a disadvantage is unable to draw realistic images. Now the raster scan is able to draw realistic images, and of course we have million different colors that can be generated using the raster scan display. And of course, as an advantage, shadow scenes are also possible here. It was not possible in the random scan, but in this case we'll be able to draw some shadow scenes on the raster scan display. Of course, these are the two main disadvantages of the raster scan. The resolution that is produced by the raster scan display is quite low comparative to the random scan. And here, of course, it's also very expensive. When it's quite expensive as compared to the other one. So the difference between the random scan have been outlined here. So the random scan has high resolution, whereas the raster scan has low resolution. The random scan is quite expensive as compared to the raster scan. So any modification, if any sort of modification is needed, it is easy to use the random scan because it's a line segment. But it's quite tough because when you talk about the raster scan, because everything is done, is converted into a form of pixels. So we have solid pattern that the random scan display comes out with, and these solid patterns are sometimes quite tough to fill. However, for a raster scan, the solid patterns is easy to fill. And of course, the refresh rate depends on the resolution. However, the raster scan, the refresh rate does not depend on the resolution or the picture. Still under the these differences, these are four main differences that are also available between the random scan and the raster scan. Only screen with view on area is displayed. The whole screen is scanned. So as I explained, when we're drawing the triangle, it's only the screen. It's only the screen with the view or the object that we want to draw is the one that is displayed on the screen. However, with the raster scan, it has to now go through it has to scan each of the rows on the screen to be able to know whether the intensity of the object is supposed to be turned on and off. So that is another disadvantage. So the beam penetration technology come under this. So, and of course the shadow mask technology falls under this type of display. The random scan does not use interlacing method, as you saw, and of course the raster scan use interlacing method. And finally, It is restricted to line drawing applications. So as you saw, and this is restricted, is suitable for realistic display, as explained in the previous slides. Now the next display, which is the direct view storage tube, which is the DVST. As you can see here, the DVST terminals also use the random scan approach to generate images on the CRT screen. So as the term says, it says storage tube. So it refers to the ability of the screen to retain the image which has been projected against it. So therefore, this avoids the need to rewrite the image constantly. So the image that is projected on the screen is stored in the storage tube, and this helps this type of display from rewriting or regenerating the image constantly all the time, as compared to the previous ones. Now, under the function of the guns that are available for the DVST, as we already said, it's also a random scan approach which generates images on the CRT. So in this case, it has two main guns. The DVST has two main guns. We have the primary gun and also the secondary gun, which sometimes we term as the flat gun. Now, for the primary gun, as you can see, is from here. This is the primary gun. The primary gun, as you can see here, is used to store the picture pattern that is supposed to be displayed. It's used to store the picture pattern. Then this, being a secondary gun, is used to maintain the picture display. So it's used to maintain the picture display. So for the DVST, although it's an example of a random scan approach, it has two main guns, the primary and the flat gun, which is termed as the secondary gun. The primary gun is used to store the picture pattern. The secondary gun is used to maintain the picture display. Now, of course, we have the collector and also the screen itself and the storage grid, which is going to store the image so that we don't have to regenerate the image again. So that is how the DVST, or the direct view storage tube, looks like. And of course, it has its advantages and also disadvantages. One advantage is the images that are created on this type of tube have high resolution. And of course, in achieving this high resolution, the cost is quite less as compared to the others. And here, as another advantage, there is no refreshing in this type of tube, because we have a storage tube holding the image that is displayed, or storing the image that is already displayed. So we don't need to refresh as the random scan is, that you have to refresh and all of that. So as a disadvantage, it is not possible to erase the selected parts of the picture. And again, it is not suitable for dynamic graphic applications. So if you want to come out with a dynamic graphic application, this would not be the best of options to use. Dynamic graphic application, meaning something being dynamic, has some sort of movement within it, so it's not really suitable for such graphic application. And of course, if some sort of part of the picture is to be modified, it is very time consuming to modify the part that has already been drawn and stored in the storage tube. It's quite difficult. Now the next one display that I want to talk about is the flat panels display. So this is an example of a flat panel display, 45-inch flat panel display. Those that have used, so we have these. You can see the flat panels that we have now. The TVs that we have do not You don't have to. You need to have this bulky type to call it to as flat panel. We have different versions that are available. These ones are heavy in terms of weight and also the power that you have to run through to be able to display the images on the scene. All right, so it refers to a class of video devices that have reduced volume, weight, and also power required compared to the CRT. So this is one. This is a big CRT of size 45 inches, and of course now we have flat panels, and in this case we don't need to have so many. We don't think about the weight. Old CRTs that are available that have bigger screen are quite weighty, or they are quite heavy compared to the flat panel display. So an example or examples of the flat panel display are small TV monitor, the calculator that we have, the pocket video games, the laptops, and also advertisement board in elevators, and also displays on doors of buildings and the rest. I mean, digital displays. So when we talk about flat panel display, there are two main types. We have the emission display, excuse me, and we also have the non-emissive display. When we talk of the non-emissive, then we are talking about the liquid crystal display, which is the LCD. For the emissive display, we are talking about the plasma and also light emitting diode, which is the LED TVs that are available. So yes, these types of cathode ray tubes TVs are quite heavier. So that is why we have the flat panel display, having its reduced weight and the rest. So the cathode ray tube, we have all types that are available. They are quite big and they are quite heavier. But with the flat panels, they have reduced volume in terms of weight and also the power that's required to help display objects on the screen. So for the emissive display and also the non-emissive display, we have the emissive display being devices that convert electrical energy into light. So that is the emissive display. An example is the plasma panel, the thin film, the electroluminescence display, and the LEDs that are available. That is the light emitting diode when we talk about the emissive display. As I said over here, we have the flat panel display segmented into two main types, emissive and then non-emissive. So when we talk of the emissive display, we have the emissive display as to be devices that convert electrical energy into light. And these are examples, the plasma and the LED displays. For the non-emissive display, these are devices that use optical effects to convert sunlight or light from any source into the graphic pattern. So an example is the LCD. So lights from any source. So that is a liquid crystal display. It uses an optical effect to convert sunlight from a source in order to display the pattern of the graphics on the screen. So that is about the LCD. So this brings us to the end